Questions? No questions? So we're talking about dynamic control flow. This is code that jumps to a location where the location is determined at runtime. One example of this is polymorphism. Kind of that polymorphism in which a method call, which is called on an object, calls some implementation of the named method, but which one is determined by the value that you type of the object. And we talked at the end of last time about how this is implemented, which is described up here. I'm going to rewrite it. So the idea, in this example, we have two classes. Class A implements two methods. Class B extends A and overrides one of those methods. And this is represented in the data, the static data of the system is the following thing. The class object for each of these classes. So that's created statically. In Java, actually, is created the first time you reference a class. There's something called the class loader. It takes the class name, sees if it's been loaded previously. If not, it goes and finds the file that contains the .class file that contains the bytecode for that, loads that in at runtime. But then once it's there, it doesn't change. And what's stored in here is all the static variables, if there are any. And a jump table. Now, because A implements two methods, there's two entries in the jump table. B implements three methods, there's three entries. The meaning of each of these entries is determined by the list of instance methods that the class implements. So A doesn't extend anything else. So it implements just two methods, ping and pong. So this first entry is for ping, and it points to the code for ping. And this is the code for pong. And same here. So this has to have the same meaning. This being a subtype of this, you know that sometimes there will be instances of this object, the actual type will be B, that will be used as if it's an A. And this means that sometimes you'll actually be using the code that thinks it has an A, but it actually has a B. So the meaning of these two things has to be the same. This has to be ping, that has to be pong. In this case, B extends ping, so or overrides ping. So that's its own implementation. But it inherits pong, so it just points to A through pong. And then it also has another control flow. So that's all the static stuff. And then when the program's running, you might say some variable A equals new A. And this creates, oh, I forgot to bring the gamma eraser. There's no use. Not really good. Not erase anything except this. So, A, new A, which, here's A, and it points to an object. Now inside of this object will be all the instance variables. In this case there aren't any, but this would be the instance variables. And also a class pointer that points to the class, the actual type. Right, so I say B to A, so that's A. And I might say also B. So here I'm just going to say the apparent type is also A. And that will point to an object. And its class will point here. So then when I say either A dot ping or B dot ping, the compiler is going to generate code, and the code is shown in, I think, RTL at the bottom of the slide, to dereference A, get to the value of this pointer, read that pointer, get what's stored at the location in the jump table for ping, which the compiler will know is at a static offset. In this case, it's offset 0. And jump, it reads that. That is an address just like we had for the return statements. It does something like this. Jump, that was the return statement. We're going to jump now to whatever address is in here. So it won't be R6, it will be some other address. And if you say b.ping, the exact same code would be generated. To dereference B, but B points to a different class. Read what's up offset 0, right? Same location, but different array, and jump to that code. Different procedure. And that's the basic idea. Any questions about that? And why is this good? Why do you like Java? Subtype polymorphism. What's the value of that? Does anyone like it? Yes. So what?
Use inheritance.
Okay. So what's the value of inheritance?
It's easier to code.
Why? Yes.
Because you can reuse code.
Right. And why is it good to reuse code?
Simplicity.
And no duplication. I mean, the main benefit. I mean, everything you said is absolutely true. I just want to throw in also this idea is that when you have the same, approximately the same code, you want to write it once. This aids maintainability and understanding. Really important. You know, this is like single point of control for data, is that if you have multiple copies of something that do approximately the same thing, and you want to change what that thing is, you don't want to have to go and change multiple locations. So if we have something that's basically something, but it might differ by the actual type of something it uses, and later on today I'll show you an example of this, then we can write code that uses subtype polymorphism. So you get inheritance, you get this idea, I can create a new thing that's kind of new and kind of old, right? So here it has, it's changed two methods and kept the same the other one. So that's inheritance. That's really nice. I didn't have to rewrite code. But actually, I think more to the point of the power of this idea is that this can substitute for this. So any place I wrote code to use these things, it can also use these things. And it will magically get a different implementation of ping. Now what's required is that this ping and this ping have the same interface, so they can be called the same. And they have, this, it conforms to the Liskov substitutability. Right? Everybody remembers that. Everyone else. I do. Right. Okay, so just don't ask me to say what weekends, what So what we're going to do, smile, that's true. That's actually, it's like a probably good difference. I just don't know. The smile is weakening. So, okay, stop. So what we're going to do is we're going to take this idea and implement it in C using everything we know about C. So basically we're going to create structures and things and have some static objects that point to the things we want to. And then introduce one new idea, which is described on this slide. And this is a new data type to you. It's called function pointer. So a function pointer is a pointer to code. And so you know that, I so wish I had an eraser. I don't suppose anybody brought with them a whiteboard eraser. Last time I even had a tissue, but I don't have a tissue. Okay, it's right here. So I'm going to kind of squeeze this in. So,
anyone tissue?
now, so you know that I can do something like this, for example. Declare a type as a pointer to an integer. And then the way that's represented is as a box that stores a memory address, and that's the memory address of an integer. And if I want to dereference that pointer and get the value of 3, how would I do that? using the variable a, how do I get the value of 3? Star a, or what? Ah, voila. Thank you so much. What else? A sub 0. Okay. So now what I'm going to do is create a variable that instead of pointing to data points to code. So now that I have an eraser over here. We're going to redo this over there. And it's the same thing. So let me just first say that when you say pointer to code, what does that mean? Well, that means I have some procedure, let's say void foo, a static procedure, and now I want a variable that will point to that, to the code. And what would it mean to dereference that pointer? Well, you might think it means go to the address of, and that's a part of it, but
Would you get the implementation?
to actually execute the code. So both of those things get you. I'm going to be using a pointer to execute code, but the code that's going to be executed is determined by the value of the pointer, not a string. Okay, so if I just say foo, that's a static call, and that's going to be just jumped to some constant address. Okay, but what I'm going to do instead now is declare a variable, and I will call it bar. So I want to declare a variable bar that will point to code. Now, what's really, really strange, but this is not the first strange thing you've seen about C, but this is really strange, is the syntax for declaring this variable. So for every other type, the syntax is, type space variable name, and then maybe space equals static initializer. But that's not true with this type. So I'm going to leave the variable name in black and do the rest in blue. So all of the rest of this is declaring the type. So what I do is I take the name, put a star in front of it, which is, star is sort of an indication of pointer. I just like what we did here. But the variable name is in the middle. I then put parentheses around this. I put a type here. That will be the return type of this function pointer. And then I have here a list of parameter types. In this case, I'm going to use this pointer to point to this procedure. This procedure has no function, no parameters. So I can use the word void in this location to say no parameters, but I can also just. So that creates a variable that can point to any procedure whose signature conforms to these two things. So that's weird, right? So that's like that. But here, the variable name is in the middle of the type. The next thing I can do is I can give that type a value. And one possible thing I can have on the right-hand side is the name of a static procedure. I can also have any expression that uses function pointers. So I can copy a function pointer to another function pointer. Later you'll see I can have an array of function pointers and stuff like that. Okay? So what that does, this assignment takes this variable, so here's bar, and has a point to the code for foo. And then I can dereference this pointer like this. So that looks just like accessing, calling a static array, but it's going to be implemented by something like this, rather than that. It's going to jump to a dynamically determined value, and that will be the value of bar. So in this case, this is exactly the same as calling foo, giving the effect of it, even though the code will be different. But if I change the value of bar at some point and execute this again, it'll jump to some other location. And so the syntax here of this being the same as that is kind of analogous to the static and dynamic arrays. So remember with static arrays, it's like that, and then that's the array. And I can say this or this to access elements of the array, but that's not dereferencing a pointer variable. It's just using the constant address to compile those access. So same thing here. The syntax for dereferencing a function pointer is the same as the syntax for calling a procedure. They're called exactly the same way. This procedure has parameters. They be listed here. If it returns something, you put that on the left-hand side. The assignment is just the variable name without the parentheses gives you access to its value rather than dereferencing it, just like other pointers. And the only thing that's weird, well, I mean, and this has to be, can't be pointed to data, it has to be pointed to code. And the only thing that's weird is the syntax.
So when you said if it returns something, you have to put it to the left, do you mean like you have to have like a variable to receive it, or?
Well, it's just like, so let's do that example. So let's say I had some function pointer like this. Say int. And maybe even it takes an integer as a parameter. And then I have some other function, foo, which is a static function. So it has an implementation that has the same type signature. If those two things are true, if the type of this matches this, then I can do this. And then to call foo using var, I can do something like this. Just like I can call foo directly. So if you're looking at this line, the dereferencing line, it looks exactly the same if it's a function pointer regular function. The differences are up here. The difference is the way you declare this thing. This is just a variable. This is actually a variable statically associated with code. Think of it that way now. And then you can do this step, which you can't do. I mean, I can't say foo equals something. Right? Can't do that. This foo is a constant address of the code. Does that make sense? Okay. So we're going to use this now. I'll leave it there for a second, but I'm going to have to erase that. To right. First is the scientific question. Which I forgot to bring up. Swishy thing. I moved from my glass, so I cannot see anything. There we go. Okay, there it is. Answer that question. B of 859. 15 seconds. Five, four, three, two, one. Okay, good. So the difference here is in the procedure go. So in the top version, let me just switch back to the slide. The top version, go. The top, well, now it's the version on the left, go calls what looks like a procedure proc. So if we now look for the name proc, you see that proc is actually a variable. It's the parameter to go. So we know that that is a dynamic call. We know that when go is called, it's going to call some procedure. But we actually don't know what that procedure is. It could be different procedures for different calls to go. So we have to now find a particular call to go. And this code only has one, and that's from main. And when it calls go, it provides as the value for that argument foo. And foo is the name of a statically declared procedure. So now we know the value of proc when it's called from back, when go is called from back, is foo, and so go will call foo. But if there was another line below that said go, bar, then the second call to go, proc calls bar. So you actually don't know by looking only at go what it's going to call. Whereas on the right-hand side, go calls a procedure named foo, and if you look for that name, we find that name associated with the statically declared procedure. So that, on the right-hand side, when go is called, it will always call foo. You can't change it. And this key idea, you can write code that's parameterized by what function it calls, is in essence what gives us, with subtype polymorphism, the ability to substitute. That substitutability is in essence just having this ability to write some code that's parameterized by what function it calls. Okay, so we're going to use function pointers now to implement polymorphism, but only after you do this. So I want you to write a function that function is either going to add two numbers and multiply them, depending on a parameter, and that parameter needs to be a function pointer, and then call it so that you can add or multiply numbers. Okay, so you're going to have one function that will call math, let's say. So we'll have a parameter. That parameter needs to be a function pointer. And then function pointer two values. And then it will you'll use that function pointer to either add or multiply like this. So I'm going to be able to say, x equals math of add 1, 2, or x equals math of mult 3, 4, and so on. Where these are named with statically declared procedures. So the procedure, the operation it does is a parameter just like the values of parameter. Okay, so write the code for this and then for adding that. Okay, so 15 seconds. Okay, so let's look at the implementation of math to begin with. So math is going to have three parameters. I'm going to call them f, which is the function a and b. So I want to be able to do this. Return f of a and b. And so a and b will be a function. It takes two integer pointers and returns an integer. So to declare that parameter, I have, so there's f. I say star f has to return an int, and it takes two integer parameters. Okay? That's the declaration of that. Now a and b are pretty simple, right? It's just int a, int. Any questions about that? So now calling math, you're going to get back an integer, and the integer you're going to get is some function that you're going to determine on a and b. So for example, if we declare the variable, the function add to be like this, then here's add, right? Add becomes the parameter in this call, the value of f. And so this call will call that function. And if similarly I wrote multiply, everything the same except that with the star there, then this call here, math, will call multiply. So the key difference between just adding and multiply, of course these are very simple things, is I can write one procedure now that will do anything. It'll add, multiply, subtract, divide. And what it does is a parameter to the code, and that's what function point provides. Make sense? Questions about that? Okay, so now, finally, we're going to use this to implement polymorphism. So here, we're trying to mimic this. So I've got, this is Java, so I have class A that has two procedures, ping and pong. Not like that. There's some code here, but we're going to leave out the information. And another class B that overrides ping with its own implementation. And add the new method called, or with, sorry. And then, some function foo that takes a parameter whose parent type is A, and calls ping. And then have some other function, say bar, that calls foo with a new A the first time and a new B the second. So we're going to try to do all of that here. We know that from what I wrote up here before, which I'm going to write again, I'm using my black pen. Switch over to blue here for this, is that I have class A, class B, which include jump tables that have pointers to the code. And then I'll have objects that are created by define these things as structs, have some static variables that will represent the class objects, write a constructor that will create the instances A and B in the right way, and then do something very similar to this syntax here to call a function that uses function pointers in the jump table and the class object to essentially do substitutability. So it'll call the version of pain it calls dependent upon the type. So the first step is to declare some types. So the types we want to declare are listed. I have all of the ones for A, and then after there's all the ones for B. So we'll just focus on A, and I'll write both A and B. So we're going to have a struct whose name is A underscore class and B underscore class. That will be the type that represents these things, right? And then the jump table here I'm going to represent as function pointers where the name of the function pointer variable is the name of the function. So struct A class. Now neither of these have any static variables. If they had static variables, those variables would be also listed here. But they only have these two things. So I'm going to have a function pointer named ping. This is going to be like this: void star ping. Now ping takes no parameters, except what you know is that in the execution of ping, you can refer to this. And this is a pointer to that object. Everybody remember this? That's actually a parameter. It's a hidden parameter. So we're going to have to make that explicit here. So I'm going to do that like this. So this will be a function that takes only one parameter, and it's type, and you'll see why later. This must be a void star, but it'll really be a pointer to a class. An instance. And I'm going to call it this V, meaning this V is virtual, it doesn't have a type. And then we'll fix that later. And then void star Pong. And the same thing for B. And I'm just going to abbreviate this now. I'm going to ping, Pong, and whip. But they'll be quite like that. So that's the type. And then I have the code. So in total, how many procedures are implemented, or whose implementation is listed in these for these two classes? A implements 2. The class B itself implements how many? 2. So this code describes the implementation of 4 procedures, right? 2 versions of ping, a pong, and a whip. And so I'll do this. I'm just going to do write out all the pings and then just list the other ones. So I'm going to say void A ping, void star this B. And I'm going to provide a little bit more here than is on the slide. I'm now going to cast that into something which I'll fill out later. And then I'm just going to print something. Right? But at this point, I can use this to refer to the object on which ping is invoked. Same thing for B ping. and also for A Pong and B. Okay, so that's the code. And the final thing I'm going to write over here is the static data. So this is the class object itself. So this is going to be a global variable that is statically declared and statically initialized to be either that struct or this struct. So I'll have one thing that's called a class table. Its type is struct A class. And it's statically initialized like this. And what that means is that, so we know if we draw a picture of this struct, there it is, right? It has two entries, ping and pong. This initializes ping. This initializes pong. So what we know is that this is initialized to point to that code, and this is initialized to point to that code. Does that make sense? This syntax? Questions about that? Similarly, we have struct B class, which is, B pong, B ping, A pong, and B width. So it is, I'm trying to stick with black for all the static stuff, but I'm running out of black. It's this table. It has three things in it. That's the initialization. So the first thing is going to point up here to B ping, and then the second one points to A pong, and the third one points to So these three things is all represent all the static stuff. So that just exists before the program's running. I've got two variable names here, global variables, A class table and B class table, that represent the two class objects. So now the next thing I need to do is write new. Now, this is also a static function. This just illustrates what I did there. Okay. Right. I need one more type. So I've got the types here. I also have another type over here. These will be the types. This is also static, but I just don't have it black. So I've got a struct A. So struct A is a type that will represent the object itself. So this is the template for all of the dynamic stuff in the class. If there were instance variables, they would be listed here. There are none. And there's going to be a pointer to the class object for this thing. So there's a pointer here to struct A class, right? One of these things, right? That is this. Oh, I erased it. That. So struct A class star, I'm going to call it class. And then the instance variables would be listed here. Same thing for B. And every other instance of every other class is all going to have a variable name class at the very beginning that will point to its class. So I can depend upon that. I can take something to struct B and cast it to a struct A. And they're both going to have class in it, and I'll use them. They'll just be different types. So now finally, I can write the code for new, which is shown here. Slide. So new A is going to return an instance of this. Now, if A had any instance variables that would be normally initialized by the constructor, those would be listed here as parameters to new A. Okay, so this is, analogous to a constructor for the class of A. We don't have any instance variables, so we're going to ignore those completely. And all I have to do now, so what does the constructor do? When you say new, what happens? I have to allocate the memory, and then call the constructor code to initialize it. Okay? So we're going to allocate the memory. I'm going to have a variable that I call object.